So we investigated the vertical asymptotes, we investigated horizontal asymptotes, and then we're going to look at this last example. So again, push pause. You can put these in your graphing calculator. You don't have to write them down, just put them in the graphing calculator and take a second to explore. All right, let's hope you had a chance to explore these. So I have them in there, and let's see what the graphs do. So we look at the first one, and everything looked fine. And then there's this little break. Oh, and another little break. And then if you look closely, there's a third break. So it's kind of weird. All of these, you see this? The graph is going along here, and we get a break. This one's going along, and there's a little break, and a little break. So each of these have these breaks, and in fact, they don't. This first one doesn't even look like a rational function. It looks like a line. So does this one here. This one looks like a rational function, but they have these little breaks. Now, we shouldn't be surprised that there's this break. And if we look at the first case, the break happens at around -2. Well, we know if you put -2 into this function, you're going to get a 0. So there is a spot where it doesn't exist. The only catch is usually we think there'd be a vertical asymptote, but in this case, it's not a vertical asymptote, it's like a hole. Same with up here. Okay, this one looks like it's at x equals 2, and if you put in 2, you'll get a hole at 0. And this one, it looks like it's at 4, because you put 4 squared, you get 16. And this one, you do end up with an asymptote, but these ones, you just end up with these little holes. So, different altogether. So these last ones, they have holes. So I wonder why this is. Well, there's a technical name for that. It's called point discontinuity. So it's discontinuous, it's not continuous at a specific point. So you'll notice that this definition says if you have a rational function where you have a polynomial on the top, polynomial on the bottom, it has a hole at x equals a if x minus a is a factor of both the top and the bottom. Okay, so apparently if within this function, if you actually factored this one at the top and the bottom, there'd be an x minus a here and an x minus a here, and that's the conditions for a hole. Now, when we read that, it kind of doesn't seem like it makes sense. It makes much more sense when we actually look at the example. So let's go back and look at A. If you look at the top, you have x squared minus 4. So I'm going to factor that and go, its difference is squared, so it's x plus 2 and x minus 2. And the bottom, well, it's already factored, it's got x plus 2. And notice that x plus 2 can cancel. And so, but it's still, x is not allowed to equal 2 because you're going to end up with 0, but it cancels. So it turns out that there's a hole at the root of the function that disappears. So if x minus 2 disappeared, then there's a hole, or sorry, x plus 2, excuse me, so there's a hole at -2, my fault. If x minus 2 had been the one that would cancel, then the hole would be at x plus 2. So the hole is at the root of the factor that cancels. And then notice, since it cancels, what are you actually left with? You're actually left with x minus 2 as your function. Well, that's not a rational function anymore. This is a line. And so it's a little different in that it looks like a line. The graph comes along and it looks exactly like the line y equals x minus 2. So there's minus 2 is the y-intercept, and it goes up 1 over 1. It looks exactly like a line, except it doesn't exist at this spot. Does the same hold true for the other ones? Well, in B, if we factor that on the top, we have a common factor of 5, so it's x minus 2. And x minus 2 on the bottom, again, you've got a factor that's the same, so it cancels. So that means there's a hole at the root at x equals 2. And you're left, in this case, with just 5. So it's equal to 5. Well, what does the function y equal 5 look like? Well, it looks like a straight horizontal line like this at 5, except it's got a hole at 2, x equals 2. And let's check the last one. Factor this one, x plus 4, x plus 4 minus 4, so difference of squares. Again, the x plus 4 is the thing that cancels, and so the whole is at x equals negative 4. This one, though, when it cancels, this divides to 1, this divides by 1, you're actually left with 1 over x minus 4. Well, that is a rational function. So that's why our third example, we'll just turn this back on, our third example still looks like a rational function, except it has that hole right there. So we've seen all the different conditions. Let's try and use it all together. So I'll give you a second to write that down, but we're going to actually investigate what the asymptotes are. Okay, so hopefully you've had a chance to write it down. So we're going to look at the first function. We're going to look for vertical asymptotes first. So we're looking for the spots where x is going to result in a 0 on the bottom. So x minus 1 can't be 0, so you do x equals 2. Chances are you're not going to write this down. You know the vertical asymptote is going to be at 2. The thing we need to practice, because I'm pretty confident we know vertical asymptotes, we've got to practice horizontal asymptotes. So we're going to look at the function, see what the degree on the top is. In this case, it's 1. The degree on the bottom, which is 1. So n equals m. So since they are the same, we're going to look at the leading coefficients. So now the leading coefficient on the top is 2. The leading coefficient on the bottom is 1. So therefore, there's a horizontal asymptote at 2 divided by 1, which is 2. And we've had our vertical asymptote at x equals 2 and a horizontal asymptote at y equals 2. Check B. Well, first when we look at it, I notice that the top can be factored. And we like things in factored form before we try and graph them. When I factor, it turns out that I've got something that cancels x minus 2. So where is the hole if the x minus 2 factors? Well, that means we must have a hole at x equals 2. Now, I forgot to look for vertical asymptotes. Well, my first gut was that there's a vertical asymptote at x equals 2 because that's what's going to not work in the bottom, but it turns out it's not really a vertical asymptote. It turns out that it turns into a hole. Are there any horizontal asymptotes? Well, let's check the n, which is the degree on the top, which is 2. M, which is the degree of the denominator, which is 1. And since n is greater than m, then there is no horizontal asymptote, which is not a surprise. We have a hole. Now, since it's greater by 1, there might be an oblique asymptote. It's not guaranteed. So for this example, there actually isn't an oblique asymptote. It's just a hole. So I'll give you a second to pause and get caught up with that before I move on to C. All right, let's try a third one. So there's the one we're going to try now. Again, we'd like things in factored form first. We have difference of squares, so it's x plus 2, x minus 2. And now we can look for vertical asymptotes. Well, there's going to be 2 this time. A vertical asymptote at negative 2 and a vertical asymptote at positive 2, because negative 2 when you plug in there is going to get a 0, and a positive 2 when you plug in there is going to get a 0. So there's 2 vertical asymptotes. How about horizontal asymptotes? Well, we'll look at n, which is the degree on the top. Well, there's no x, so the degree is 0. Bottom, m, the degree on the bottom, well, you see x times x, or just remind ourselves back here it's x squared, so the degree is 2. So n is less than m. That means the bigger number is on the bottom. And what happens when you have a really big number on the bottom of a fraction? Well, it essentially goes to 0. So we can go back and check our notes that says if n is less than m, if n is less than m, the bigger one on the bottom, then the horizontal asymptotes at y equals 0. Oh, sorry. There's that case right there. N is less than m, so we have a y equals 0. And the last one I'm going to do, d f at x equals x squared plus 4 over x plus 1. We try and factor. Looks like difference of squares, but it's not. It's a plus, so I can't factor it. So I'm going to go off and just check the vertical asymptote. What value for x is going to get me a 0? So it's -1. So there's my vertical asymptote at x equals -1. And then we check the horizontal asymptote by checking the degrees. The degree on the top is 2. The degree in the denominator is 1. So n is greater than m. That means there is no horizontal asymptote. I notice that it's bigger by 1. So therefore there's probably, or there may be, an oblique asymptote. Remember, we'll investigate those later. All right, so you've had a chance to really think and explore through this. I know it's been long videos. You can try a little bit of practice with this. Really, it's just getting used to, especially the horizontal asymptotes. So number 1 to 3. And just a little note, when you're doing this, if you look at 2i, there's a mistake. Okay, the back of the book says something else. The actual horizontal asymptote is at y equals 2. So just when you're doing this, page 262, oops, 1 to 3, when you get to 2i, notice there's a mistake. Now, do a little bit of practice with this, but we're going to practice these every time we go off to sketch these functions, which is what we're going to be spending the next couple of days doing.